Okay, so number 9, peripheral vascular vasodilation of lower extremity arterioles tends to do what? Okay, so if we vasodilate, what happens is the pressure reflections and the flow reflections both decrease. So let's look at these answers. Increase femoral artery mean blood pressure. No, it won't do that. It'll actually decrease it. Decrease pressure pulse reflections. Yes, it will do that. But let's look at the others. Increase peak systolic pressure in the femoral artery. No, it will decrease it. Increase flow pulse reflections. No, it'll decrease it. So whenever there's a vasodilation, it decreases pressure and flow reflections. So distal to hemodynamically significant stenosis in a femoral artery, you would expect. Okay, so we're saying distal, so further away. So here's our stenosis right here, and we're going this way, and so we're talking about distal, so be beyond the stenosis. So what's going to be beyond the stenosis? We're going to have decreased pressure. We're going to have decreased pressure reflections, I guess, and we're also going to have decreased flow reflections, which I don't think I can put on the page. Okay, so a okay, so you would expect systolic pressure to be decreased. I think that's probably true. So I hate it when the answer is the first one, then I don't get to go through them, but okay, I think that is the answer. B, systolic flow to be increased. No. So if we're going this way like this, there won't be increased flow. There'll be decreased flow. There'll be increased pressure before the stenosis, but no, there'll be less flow. So we can get rid of B. C, pulse pressure to be increased. Okay, so if we're talking about right here after the stenosis, pulse pressure, if you remember, it's the difference between systolic and diastolic. It'll either be the same or it'll be decreased, but there's no reason that it would be increased. So C is not right. And increased rate of rise of the pressure pulse, again, past here, no, that's not going to happen, so we can knock that one out. E, a narrowing of the pressure pulse width. Let's think about this one. You can make an argument for this one, but it probably would stay the same. I think that A is a better answer. Systolic pressure to be decreased. It would definitely be decreased. Okay, number 11. A patient's systolic/diastolic blood pressure by this word here, which is the blood pressure cuff, is 140 over 110 millimeters of mercury, and his cardiac output is 5 liters per minute. His central venous pressure is 10 millimeters of mercury, and his heart rate is 120 beats per minute. Which of the following is the closest to his total peripheral resistance? Okay, so what's going on here is we're going to use that equation. Flow equals mean arterial pressure minus central venous pressure, and sometimes you can leave off the central venous pressure because central venous pressure is almost zero usually. Central venous pressure is the pressure right before the right atrium, so that's going to be one of the lowest pressures in the body. And then TPR is below that. You divide total peripheral resistance. Okay, so we are trying to solve for total peripheral resistance, and we find out that cardiac output is 5 liters per minute. So I'm going to put a 5 there. Then we have, here's our systolic and our diastolic. So if you remember, to get to mean arterial pressure from this, we have our systolic, our diastolic. We go 1/3 of the way back to it, and then that's going to be our mean arterial pressure. That's an estimate of it. So 140 minus 110. 140 minus 110 equals 30. And so 1/3 of 30, so if we divide this by 1/3, it equals 10. So we would add 10 back to our diastolics. So we'd have 110 plus 10, which is 120. So we'd put in 120 for mean arterial pressure. Let's see, then we have, central venous pressure is this right here. So we'd put a 10 for here. And then this is what we're trying to solve for. Okay, so we did not need this number. That's just there for the fun of it. Okay, so 120 divided by, 120 minus 10 equals 110. And then, so what we would do, and I don't have enough space on here to do this, is we would multiply both sides by TPR. So what we'd end up with is TPR, let's see, times 5 equals 110, and then we would divide both sides by 5, which would give us 22. 22 is the answer. Okay, number 12. Which of the following is a true statement? Okay, so let's see. This is kind of a... Let's see. So let's go through them. So pressure waveform in ascending aorta is narrowed by the presence of reflected waves. I don't think that that's true. I'm trying to think about the pressure waveform. If you remember the pressure waveform, it does narrow, but it narrows distally. The further away from the aorta that you go, the pressure waves start to narrow. The flow waves narrow in the aorta, I think. But either way, A is not right. Okay, so B. Systolic flow increases in the femoral artery because of reflected waves. Let's think about this one here. I don't think it does. Let's see. I think that if you wanted to make this a true statement, I think you would need to make this the coronary arteries. The coronary arteries benefit from reflected waves because, remember, the reflected waves come back and they create that dicrotic notch in the aorta, and the coronary arteries are perfused during diastole. So I think the reflected waves benefit the coronary arteries. Okay, C. Systolic pressure in the femoral artery exceeds that in the aorta due to reflected waves. Let's see. And that would be true because of reflected waves, the further away you get from the heart, the higher peak you can get because they, if you remember we have two types of waves. We have pressure waves and we have flow waves. And the pressure waves, they're in phase, and so they, if you think about a tube and you have pressure going this way and pressure going this way, and they collide, they're going to add. Whereas flow, if you have flow going this way and flow going this way, they're going to subtract. So pressure waves are in phase, flow waves are out of phase. So C would be correct. D, let's just look at it anyway. Shape of peripheral flow pulse in large arteries depends mainly on blood viscosity. Let's see. And I would say that this is incorrect. Probably what you want to, if you put compliance, that would probably be what would make this a true statement. That's a good way to kind of take tests. Is if there's a better word there, that's how you can rule out that answer. Okay, number 13. Normal pulsatile blood flow reversal in the peripheral arteries of the leg is mainly due to. Okay, so if you remember the flow reflections in the, as you get further from the heart, here's what the waveform looks like for the flow. So I'm going to draw a line through here. So it's like the blood goes forward, and then it reverses, and it's actually, this is 0 right here, so it actually reverses for a little bit and then it goes forward again, and that's actually the normal flow wave in the peripheral arteries. Okay, so let's see. So let's look at our answer choices. Okay, so pressure reflections that are in phase with the forward flow wave. Okay, so the reversal has to do with the flow wave, so we can take away A and B because pressure is not what we're looking at. Okay, so flow reflections that are in phase, okay, they're not, they're out of phase, so it's D, flow reflections that are out of phase. So again, it's this whole principle of that we have these flow reflections, and if something's flowing this way and is flowing this way, then when they collide, the flow is going to slow down. And this is what the flow waveform looks like. It's like this, it goes like that, and like that. So this is where it's going its fastest, then it goes and it actually reverses slightly, and then it comes back and goes forward again.